Okay, so have your notes out. All we need to do is just finish this up right here. I said we'd look at this a little bit more in depth. Yesterday we did several graphs. We had this nice artwork here. I was complimented on that. I appreciate that. We had some funky names for these things. So we're going to talk about this one again, and I'm going to show you how you can get your calculator to graph these. Polar graphs we can make some really cool graphs using polar functions. In fact, I've got a bunch right here. So we're going to take a look at these in just a minute and see if we can figure out how they work. But let's go back here. And let's take a look at this one again. So let me just a reminder of what we did. We said that doing this the way I taught you a couple days ago, this is a pain in the butt to make a theta r chart, to plug in angles and figure out what the radius would be when you turn to that angle. But rather than making a chart of these, we can actually graph each one of those functions. And this is a picture of every single point that you could possibly put in a theta r chart. So then you can look at it and you can pick out important points, like this point right here. We turn to 0, go 0 units. Turn to pi fourths, go 3 units. So that's this one right here. And we notice it gets larger the larger the angle is. So that's how it swings out right here. And we said, well, this would be a pedal pointed in this direction right here. Even though this represents quadrant 2 from pi halves to pi, because the radius is negative, that's why we get this pedal pointing over here in the exact opposite direction of quadrant 2. It's just a heck of a lot easier to look at this graph in Cartesian form and then relate that to what it would look like if we transfer all those points over to the polar plane. Is everybody good there? So we did. What's that?
Who figured this out?
What do you mean this?
Who made like a polar
the
graph?
whole system?
Yeah, that's crazy.
Well, they figured that there are some things that are good by figuring out the horizontal part and the vertical part, keeping those separate, like x's and y's, the vectors that we've been doing. And then they also figured there have got to be some coordinate systems that are better by having a central point and then saying where you turn and how far you go. Like if you think of where you'd locate something, in the universe or something like that, that's probably not best represented with an x and a y. It would probably be best if we said, hey, turn to this direction and go that far. Okay, so it's just a different type of coordinate system that's more advantageous in some settings.
So on the universe thing, would they also have like a z-axis then, so that you could have
They
the
do, and
two-dimensional
then
have
and then they're not. Then they're not.
eccentric?
So we deal with 2 dimensions because they're relatively easy and we can get used to that. These are called polar coordinates when we have a central point, and then all we can do is just turn to a specific direction and go that far. If we were to do it in 3 dimensions, they're not called polar coordinates. They're called spherical coordinates. Okay,
Pretty awesome.
it is pretty awesome. Okay, and there are some things that's really well suited for. Okay, all right, everybody good there? Okay. All right, so we came up with some fancy names for a few of these. We had a cardioid and we had a lemmason. There's not really a fancy name for this other than we could call this a rose. So we could keep that in mind. That's a really pretty rose, by the way. We can have them with lots of petals. And as I'll show you in just a second, we can have petals that are different shapes and in different directions and that sort of thing. You don't have anything that complicated, but you do have to keep in mind those formulas that allow us to change from rectangular to polar and polar to rectangular. There are 4 of them. They were in the box on the first page. And then we did this problem right here. We said this one's a bit more sophisticated than the ones that we were dealing with before. And the problem with this was we don't have a plain old r. We actually have an r squared. So what we did just to kind of get a flavor for how this would work is we said, well, let's just ignore the r squared. Let's just pretend like it's an r. So we can graph something that has a cosine with an amplitude of 9 and has been sped up by a factor of 2. So the period is only pi rather than 2 pi. We did this in degrees. So we graphed that and we got this shape that looked something like this. And then we said, well, it really is r squared. So what we did is we took the square root of both sides. So when we took the square root, it shrunk from 9 down to 3, 9 down to 3, and 9 down to 3. And for this part that was over here, you can't take the square root of a negative, so we don't have any points there. But then after we got done with this graph over here, we said, well, you do have to account for the plus or minus, so really there would be a piece here, and a piece here. okay? So what ends up happening is we end up making this shape. It actually happens twice, and I'm going to show you that it does happen twice, and it happens at the same time. So really, if I turn to this angle of 0, I really should graph a point that's 3 units away in the positive direction and 3 units away in the negative direction. So I really should graph this point and this point at the same time. And at the same time, pardon me, that I'm tracing out this, I should trace out one that's in the exact opposite direction. Okay? Again, really complicated graph here, but we're going to have the calculator do this in just a second. I am going to give you the name of this. This is called a lemniscate. A couple of years ago, they have typically put polar functions and polar graphs on the final. A couple of years ago, they put one on there. They had you label a couple points, draw an accurate graph, label a couple points, and then they wanted you to name what it was. You know, the names are important if you're studying these all the time. In the grand scheme of trigonometry, is the name of a polar graph particularly important? Not in my opinion, okay? So let's have the calculator do this. So grab your calculator real quick. We're going to have it produce this graph right here. So here's what I want you to do. Go ahead and turn it on and hit the mode button. And we need to change a couple things. We're going to try and keep this as easy as we can. We're going to do this in degree mode, so make sure it's in degrees. Come down right below degrees, and there's function, which it's normally in. This is parametric, which we're going to learn about next time. And this is polar, so you're going to highlight polar and hit enter. And then you don't have to do this, but on this particular example right here, example 14, we want to put this in what we call simultaneous mode. So what that's going to do is any that we put in the y equals menu, it's going to graph them all at exactly the same time. So we're going to see a bunch of graphs at the same time. So we're going to hit enter. Everybody get that? Okay. If you hit the y equals menu, if you haven't done this before, change the mode of your calculator, this looks different. You'll notice that it doesn't say y equals anymore. It says r equals. It's all set up to accept a polar equation. This has to be a polar equation in terms of theta. Now, if I start typing this function in, so this was square root, because remember, it's got to be a plain old r, not an r squared. So square root, and then I'm going to do 9 cosine 2, and then if I hit the what used to be the x button, you'll notice it has an x, a t, and a n on it. That corresponds to the different graphing modes that your calculator has. So if I hit that button, it no longer puts an x in there, it actually puts a theta. Close the parentheses for the cosine, close the parentheses for the square root. You with me? Okay, now we want to graph this on a plane where we can see roughly this shape right here. So I'm going to do something here. I turned my axes off for some reason. Then I'm going to go to the window button. And you'll notice in the window button, it doesn't just have x min, x max, x scale, y min, y max. You're not just setting up the window. We're going to set up the window in just a second, but we have to tell it, hey, what thetas do you want me to plug in? Well, starting with theta equals 0, that's probably a pretty good idea. Remember, we put this in degree mode, so this would only go from 0 to 6.28 degrees. If this were in radians, it would go all the way around a full circle, but this is in degrees, so let's change this, and let's go at least to 360. So 360 degrees. And let's tell it to pick a point or pick an angle, let's say every 10 degrees, okay? So we're going to start at 0 degrees. We're going to start by pointing toward the positive side of the x-axis, if you will. And then we're going to go rotate 10 degrees, plug it in, see what my radius is. Go to 20 degrees, 30 degrees. So it's going to pick 36 points as we go around the circle. Good there? Okay, and we'll change that in a second, and I'll show you what that does. Now, this isn't a very big graph. The largest radius is 3. So let's do this. Let's go from -4 to +4. That makes sure that we've got enough in each direction. The scale is going to be 1. And then for the y minimum, I'm going to do -3 to +3 because that, remember, our little calculator window is wider than it is tall. Okay, any questions there? And I put the scale to be 1. Okay, now I'm going to hit graph, and you watch what happens. Okay, now that doesn't look exactly like we had here. So what I'm going to do is I'm going to change this. So I'm going to come back here. We're going to go to Window, and we're going to make it pick points more often. It looked like that middle part was incomplete. Your calculator's pretty dumb. It does exactly what you tell it to do, okay? And if we pick 10, it turns out that it doesn't get right back to the pole. We never have a radius of 0. So I'm going to do it every 1 unit, or every 1 degree. So I want you to watch what happens here. Before we picked 36 angles as we went around the circle. How many is this going to pick? 360. Now watch what happens. This little worm cursor figure right here up in the corner tells us that it's actually working. It's trying to graph something. It's not graphing anything right now. You might want to think about why. Then it goes around, keeps graphing that stuff. Okay, now watch. It's trying to graph something, but nothing's showing up over here. And now it starts graphing again. Okay, so is this the right shape? It is. Can anybody tell me why it stopped graphing for a minute? Austin.
The points were so close to the center that it doesn't show up on the calculator.
That's one theory. Caitlin?
You can't graph the negative or something, so it was the empty space between.
Okay, it's this stuff right here where we were trying to find the square root of. It knew the cosine of whatever the value was negative. You can't take the square root of a negative, so it doesn't graph anything. Okay, and we can actually check this. I'm going to change this back. I'm going to do, let's go every 15. You know, that did it really fast. And what's different about this shape as opposed to the one I did here and the one that was just on the screen?
More pointy.
It did it faster and it's more pointy. That's a great word. It's more pointy. Okay? Pointier, I think, is the technical English word there. Okay? So it's pointier because we picked fewer points. All it did was find a point here, find a point there, find a point there, and it did exactly what I told you not to do. Don't draw. What's that?
Wouldn't that make it less pointy? Pointy, less pointy.
Oh, I see. Yeah. Marcos Lopez, everybody. Okay. So it picked points and then it just drew straight lines from one to the other. It didn't acknowledge the fact that, you know, it gradually changes. And we can actually make this a little bit more severe. I didn't do this with the class earlier, but watch what happens with this. Nothing. Anybody know why?
Because it just has the point there.
All the 45s are at 0. Okay, watch what happens if we do this. Let's play around with this a little. Let's do 60. Anybody know why it does that?
It's in between when it's not existing.
It's actually, yeah, there are a couple places where it's non-existent and it's also on the axis. If we remove the axis, you could see a couple of points. Let's do this. Let's go back here and let's make this 25. Pretty stupid, right? So don't just put points on there and connect them with straight lines, okay? Realize that it changes in kind of a gradual fashion. But if I go back here and I put this down as 1, and then I'm going to come back here, and remember we said we do have to account for the negative part of this, that when we take a square root we get a negative. So I'm going to come down here and I'm going to put a negative of that exact same thing. Okay, now watch what happens this time. Remember I said that if we did this correctly, we'd be graphing this piece along with this piece at exactly the same time, because this would be 3, this would be -3. This would be 2, this would be -2. So even if I point over here and I go 2 units, I really should graph another point in the exact opposite direction. So watch what happens here. And there it is. It's going to make the whole thing. It's trying to graph right now, and what it's trying to graph is this stuff right here. It's going to pick up in just a second again, and it's going to start here, and it's going to start over here. And there it is. Okay? All right. Any questions? Okay, I'm going to stop this because it'll be faster if we do... Okay, I'm going to change this to 10. Have it graph it really quickly. And watch right here. If I hit, whoops, let it finish. I'm going to hit trace. The angle's 10 degrees. There are the x and y coordinates. So it kind of does the conversion there for us. Okay, notice when I plug in a 50, 50 would be right here. There's no point. I don't get another point until I get to past 135. Okay, everybody good there? Okay, any questions? Okay, now I want to go back here and I want to look at these last two examples. And if you understand how polar coordinates work, I'm hoping this is pretty easy. We've already graphed this one, but I want to look at this in the context of how these work. What we know about, gosh, if I just graph the radius function, what is the radius function on this particular one right here? It's 2. It's always 2. So if I were to graph it here, it looks like this. So no matter where you turn, you always go 2 units. So if I turn to 0, I go 2. If I turn to 30 degrees, I go 2. 45 degrees, it's always 2, so it looks like this. All right, sort of like that. Okay, got the idea? Okay, now I'm going to scribble this out for the time being. If I just drew 2 again, I'd have a circle of radius 2. So here's the change that we made to this one. I took a radius of 2 and then I'm going to add a cosine to it. Well, cosine's going to add, let's see, it's going to add 1 or subtract 1 at the very most. And what about the period of cosine 6 theta? Yep, 360 divided by 6. So that's going to be 60 degrees. So it's going to make a cycle every 60 degrees. So if this is 360 degrees right here, okay, here's my center line. There's my radius of 2. It starts up here at 3 and it does this. It does a cycle here. There's 2, 3, 4, 5, and 6. That's really ugly, but you get the idea, right? So it starts out with a radius of 3, gets to a radius of 1 at 30 degrees, and then back up to a radius of 3. So it does this. And then it does it again in the next 60 degrees. So it goes like this. And in the next 60 degrees, it's going to do the same thing. And in the next 60 degrees, it's going to do the same thing, and same thing. Okay, now that is a really ugly looking snowflake or something like that. But do you see how the radius function, how it varies from 3 down to 2, down to 1, back to 2, up to 3, and so forth? Starts at 3, down to 2, down to 1, back to 3, down to 1, back to 3, and like that. Does that make sense? Any questions? It's a pretty complicated shape. It's not in your section, but it's pretty easy to understand if you understand this graphic approach to making a polar graph. This Cartesian graph here, we translate those points and put them onto the polar plane. Everybody good with that? Okay, I'm just going to put this in the calculator really quickly just to make sure we got the right thing. So I'll go back to the y equals menu. I'll clear both of these off, and I'm going to put in 2 plus cosine 6 theta. And I'm just going to say, whoops, let's change the window. Let's do this every 5. And there it is. Okay, any questions? Okay, you'll notice we never went through the origin because the radius was never 0, and we didn't go in the opposite direction because the radius was never negative. So it was just point in that direction, go that far, and all we were doing was basically drawing a squiggly circle, a circle that has 6 waves in it, 6 wave cycles. Does that make sense? Okay, so let's take a look at a couple that are, I think, a little more interesting than that. Let's take a look at something like this. Here's the function, 1 minus, and let me blow this up just a tad. So it's 1 minus 2 cosine 4 theta. So we moved it up 1 unit. Here's the center line. The amplitude is 2. We flipped it over and we sped it up a little bit. It does 4 cycles in 360 degrees rather than just 1 cycle. So it starts down here and goes up like this. And you'll remember what I said about what happens when we start here, get big and then close that off. When we start at 0, get big and then go back to 0, it makes a pedal. So look at this 2 and 3. There's 2 and 3, there's a pedal. Look at this one right here. It's a pedal, it's smaller, and notice that it's below the x-axis. So when we go out here and make this big pedal between, say that's 30 degrees and 60 degrees or something like that. Okay, when we go out here and make this pedal, this one is going to be a smaller pedal in the opposite direction of pi halves. So that's why we get this one right here. So here's the shape. Starts right here. There's 1, 2, 3, 4, 5, 6, 7, 8, 9. Oops, where are we? 10, 11, 12, 13. Okay, does that make sense? Pretty cool shape right here. No more complicated than the other ones if you understand this is a picture of every single point you could possibly plot from an XY table or a theta R table. Any questions there? Let's take a look at this one. This one I think is kind of interesting for a couple reasons. Here's the function. You'll notice we did something different than this one than we've done with all the others. What did we do to the period? Okay, we divided theta by 2, so what does that do to the period? Stretches it out. It slows down the cycling time. So it's not going to make the entire shape in 360 degrees or in 2 pi units. It's actually going to take 4 pi units to make the entire shape. And we get a pretty funky shape out of this. When you turn to 0, how far do you go? 4. By the time you get to pi, it shrinks down to 0. So start at 4. Gradually, as you turn around the circle, get smaller and smaller and smaller. There is this piece right here. Okay, start at 0, get as big as -4, and then back to 0. This is going to make a pedal type shape, but look how it does it. Because it's negative, we're always going in the opposite direction, so it makes this big thing right here. Notice that the largest radius is -4 on this particular pedal, and we do that when we're pointing at 2 pi. So even though you're pointing at 2 pi, we actually graph the point over here. And then we finish it up with that little guy right there. Pretty cool shape. Not that hard to figure out if we look at a graph in Cartesian form and then translate that into its polar form. Yeah.
So I just graphed it, and you have to put in a -4 cosine theta over 2 to get the other side of it. Why doesn't it graph both?
So we'll answer that question. Here's what Greg did, and you can follow along if you want to. He put this in his calculator, and he did 4 cosine theta divided by 2, and he graphed this. And if we hit graph, we want to make this a little bit bigger. So let me stop this. We're going to go, let me go -5 to 5 and -4 to 4. That'll be big enough to fit this on there. So here's Greg's issue. Doesn't do the whole thing, right? We only went to 360. Okay.
Yeah.
Greg's solution was, well, let's come back here and let me put a negative of that, and that'll graph the bottom half. But if we look at this, if we consider this right here, we haven't even done the entire shape. We've only done to 2 pi. We've only done to 360. If I want the rest of it, so let's remedy that. Let's go back here, and all I need to do is say, go to 720 and graph it. And then it's going to do the entire top part of it. Or really, we only get, going from 0 to 2 pi, we only get from here to pi. And there's the whole thing. Does that make sense? So one way you could know how far you'd need to go, like how many angles you'd have to plug in, would be to consider the period of the function that you're using. In order to make one entire cycle, we've got to go from 0 to 4 pi rather than just 0 to 2 pi. Okay, anything else there? You could make up almost any trig function for this radius, and you could probably figure out roughly what it would look like. This problem right here, I actually had a class 2 or 3 years ago say, hey, what if we did this? And they just made this up we figured this out and then translated it over here and had the graph in a matter of minutes. Can you imagine doing this by picking thetas, plugging them in, and figuring out the radius to go with it? It'd take forever. Okay? All right. Any questions? Okay. Any questions from 6.4? Have you started 6.4? We're good? Okay, we're gonna, yeah.
How do you graph number 52?
What is 52?
R equals 2 plus cosine.
Okay, well, I'd start with this, right? It's been moved up 2 units. Okay, it's a cosine, so that would start above. We haven't vertically flipped it or stretched it or anything, so it's going to start 1 unit above the midline. So it's going to be here. Then if we mark the middle and the quarters, it's going to be here, down to here, back to here, and back to here. So something like that. So this is going to be, and we can do this in degrees if you want. So if this is 360, this is 180, 270, this would be 90. So I'll make these fat so you can pretend I graphed that correctly. And again, there's polar graph paper on the website, and I think they're big enough, and they've got few enough lines that you can still see the points that you'd need and all that sort of stuff. So if you turn to 0, how far do you go? 3. 1, 2, 3. If you turn to 90, how far do you go? 2. And it didn't go straight there, right? Don't be stupid. Starts here and gradually gets smaller. And by the time we turn to 180, what is it? It's going to be 1, okay? Gradually goes to 1. When you get to 270, 2, 1, 2, gradually got bigger. And when you get to 360, back to 3.
This is supposed to be a lemma song.
This is a lemmason, okay? No inner loop, okay? A lemmason either looks like this, so if I draw one oriented the same way, sometimes they have inner loops. Boy, that's really ugly. I'm going to have to redo that one. Okay, that would be a lemmason, or what this one did is the radius got smaller, but not small enough, and it certainly didn't go negative, okay? So what it ends up being is it's kind of like a circle with the side that's been smashed in a little bit. It's just kind of been flattened off, okay? Yes, and I'm from Idaho, so I appreciate the reference. It does look like a potato. Good? Okay. All right. So that's it then, right? Okay. A couple things. The test is next Wednesday. The final is the Wednesday after that. We're going to finish the course tomorrow with doing 6.5. I'm going to give you a quiz right now, and that quiz is going to be due on Monday. Okay?